Okay, good morning, students. So today, uh, if you will, we are going to discuss about Schottky junction. Schottky diode. Probably, it might be the first class. Okay, I need to have one more class. I guess. Okay, so we already had a discussion about PN junction diode, right, in our last semester, and we had a fair knowledge on it. Now here, first of all, thing is that why you need Schottky junction diode. Okay, the major, if you can remember your PN junction diode concept, you can you can just recall it, and you'll find that the PN junction diode, you have to deal with two type of carriers. One is actually majority carrier, another one is actually minority carriers. Okay, and your current, like current, mainly due to of your mainly diffusion, and there's some drift part also. So you can see it's kind of drift diffusion things are going on here. But here in the Schottky junction diode, the good thing is that it's all about the majority carriers. Okay, and you know the majority carriers speed, majority carriers actually responds very fast to your applied excitation. Here in our case, it's actually voltage. And that's why its speed is really, really high, larger than your PN junction diode, which will see immediately or today's class, okay, conceptually. Today we are going to actually frame the all about Schottky junction diode um, in details, okay, which normally not there in the book. Normally, there are few special kind of books are there where you can find all these things, but normally people normally avoid this type of things. I don't know why. So let us start with very simple things, like just one thing that you know the Schottky junction diode means, like you have a metal, you have a metal, and you have a semiconductor. So it's like a metal semiconductor junction diode. So metal semiconductor, I can write junction diode. So let's draw it and try to understand. Okay. SC for my case in semiconductor, let's assume n-type semiconductor. Okay. And here, let me discuss about metal part. So, you know, the metal doesn't have any, so you have a, so metal doesn't have any kind of band gap. So it is a kind of simplified version that I'm telling, okay, just to uh, get a feeling of metal. So one thing, it is very clear. So suppose you have, you see, what I'm trying to tell you, the metal doesn't have any band gap. So in this case, what I can understand, what I can assume, that EC and EV kind of same. First of all, you may ask like whether, like, can you tell it is a conduction band or valence band? That is another question, but forget about this part. I just try to tell you that how it looks, that band gap or band diagram for metal. Just to see, just to plot this band diagram, so you can, whatever I'm telling, if you can remember the step by step, then you can plot it. I mean, at least you can understand. Okay. So first you think that metal doesn't have any band gap. If it doesn't have any band gap, so conduction band is equal to valence band. Right? So what I can understand, the EC and EV are actually merged together. Okay. Similarly, you see the metal case, the carrier concentrations. If you see the carrier concentration is tremendously high, 10 to the power 22 or more than that. Okay. So in this case, what do we know? What do we know from our PN junction perception, that if you increase the carrier concentration in your particular semiconductor type of things, what will happen? Your balance, your Fermi level, okay, slowly actually moves to your conduction band. And if it is a very high, suppose the number of carriers are very high, so what you can see, like your EF is so close to EC that hardly to distinguish. What I'm trying to see, so you can tell that EC is equal to EV. That is due to there is a no band gap. Similarly, it is also, I can write your Fermi level EF also in the same case. Why? Because it is having lot of carriers. Okay. So what is the assumption that I have taken? So I have taken multiple assumptions. One great assumption that I have taken, that EC is equal to EV, fantastic, and it is and EC is equal to EV and EF. So EC, EV, EF in the same line. That's what I'm telling. Okay. So please remember these things, and it's very important because this is the only way I feel like, what I feel like to remember the metal band diagram, okay, the light of semiconductor. Okay. So if you have a good knowledge on semiconductor, you can easily draw the metal band diagram. And let us draw it here. Then you'll clearly understand. So let us draw. You have a metal, okay, and you see that you have a EC, you have a EV, and you have a EF. All are in the same line, okay, correct? So all are same, so that's what I draw. And let's draw semiconductor. So what's my semiconductor? So and you have semiconductor fine, n-type semiconductor. Suppose you have a EF over here, you have a EC over here, you have a EV over here. Again, I'm telling you, this is a, now you can ask like, what is my, so I have taken one side metal, what's about the other side semiconductor? So one thing that I have taken, that you have a, like if this is my EF and you have a band EC and EV exactly middle, okay. So this position of semiconductor can be down, position of semiconductor can up, or anything can happen. So whatever, you don't bother about this part. If you follow couple of rules, then whatever may be the position of this semiconductor, you don't need to worry, because you can draw the Venn diagram. Okay. So only thing is that you need to follow few rules, that's all. Okay. And based on the position of the Fermi level, position of the semiconductor, then based on the position of the semiconductor, whether this metal semiconductor either ohmic or Schottky. Both means like if there is a particular position of semiconductor with respect to metal, it becomes Schottky junction. Now the same semiconductor, if the position shift up or down, it may depend. It may actually act as a ohmic contact, which will be your homework. But let me discuss about this part very carefully. Then I think the other part you can draw easily. So there won't be any issue on it. Okay. Now what I'm going to do further. So now another thing is very, very important, which you also have to be very careful. That is actually vacuum level. What is vacuum level? Vacuum level. Okay, let us draw the, okay. Okay, before I draw the vacuum level, let me explain. There is one important term or two important terms. That first term is called work function. So work function for metal. What is work function of a metal? So work function of a metal is like the minimum amount of energy, okay, needs to take one electron from metal side to the to the vacuum side. What I'm trying to tell you, suppose you have a particular metal. So this is a pen made of paper, metal. Okay. Now this pen is having a lot of electrons, free electrons. So what is the minimum amount of energy I need to do, or it's required to take one electron out of this metal influence? So the moment you take one electron out of this metal influence, then this electron will act as a free electron. Look at this thing concept. When this electron is in the metal, it's not a free metal, a free electron. When electrons are there in the metal, it's not a free electron, because this electron is residing in metal under some influence, because this electron is experiencing a force between the proton and this electron, no, right? Because suppose it's a steel or whatever, it is having some atoms. So atoms is having some proton, some electron. So whatever electrons are there, it is experiencing a force due to proton or other proton, whatever. Just 1 minute. Hello. Yeah, Arun. Sorry, what? Yes. Okay. Okay, then what? Okay. Okay, thank you. Okay. Arun, I'm taking the class. Can I reply you 11 o'clock? Okay, thank you. Sorry. So that's what I'm telling. So one electron is in their metal, means electron is influencing. So the electron is under the influence of this metal, proton, metal atoms, or metal nucleus. Okay. Now what I'm trying to tell you, that electron is under influence of this proton, no, inside this metal. When you take out this electron out of this proton influence or out of the metal influence, then you can tell it is a free electron, right? That's what I'm telling out. So metal work function means, work function for metal means, like you have a metal, what is the minimum amount of energy we need to take one electron out of the metal influence. Now, so out of the metal influence becomes a kind of free electron structure, right? So like to define this kind of things, so what people have defined one more reference level called the vacuum level. Let me write VSC. Okay. So, and metal work function. So what I'm trying to tell you now, if you try, if you just take out, I'll do the other one. Huh? If you take one electron out of this metal influence, so that is my work function, which has been represented traditionally by phi m. It is telling you about that you have a metal which is staying in the EC or EV or Fermi level, whatever of a metal surface. Okay. When you take out this electron and set it as a free, okay, the amount of energy you need to give, that is actually phi m. It is actually energy scale, right? Phi m. Now, same thing for semiconductor, but here it's my personal reference. So I'm not prefer. I don't want to bias you, but I don't want to like to define work function for semiconductor. For an example, like work function of a metal is a kind of constant value. Okay. But work function of semiconductor is not a constant. Why? Work function of a semiconductor, if you assume, you see that it means you need to have something from EF to, so EF to vacuum level. You have a one electron in the semiconductor, okay, and if you take this electron out of the semiconductor influence, you need to give some amount of energy, and that amount of energy called the work function of semiconductor. I personally not recommend it. Why? Because this is not a constant value. Why? Because the moment you change your doping concentration, your Fermi level position will change. As that means your work function of semiconductor is a function of doping. Huh? So if you really don't have any option, then you consider a term called phi s. Otherwise, don't like, better not to consider. I am not recommending. Okay. So what I am recommending, but I am very confident, and you see the whole my discussion based on these things. What I am recommending another parameter called the chi, electron affinity. I think that is good. Why? Because the position of conduction band and is actually kind of fixed. And what I'm trying to tell you, this is why it is like why I'm preferring to have electron affinity as a constant parameter, because for semiconductor your free electron is in on conduction band. For semiconductor, your free electron is on conduction band. So if you want to take out the electron out of this conduction band, if you want to take out the electron out of the semiconductor, means you are taking the electron out of the semiconductor. So what I'm trying to tell you, that if you want to take out the electron out of the semiconductor and to make set it free, it means you are taking the electron from conduction band and then you force to set it free, right? So what I'm trying to say, so this amount of energy, what I am just preparing, it is actually, and that's what I'm writing is chi. So here I am writing that two parameter phi m work function of metal and chi affinity. So this is chi's electron affinity. Okay, and other parameter I don't need to tell about it because you know this part. Eg. Here, if you go books, Treatment Banerjee and lot of books, Okay, they are considering this case in the following way, which I am not recommending, but you can think about, if because you have to read the book. So phi m greater than phi s. Look at that. Don't confuse on it. So they have considered electron. No, they have considered work function of semiconductor, which they are writing phi s and phi m. So what you means, like phi m energy is higher than phi s. So okay, so here you, so whatever I am discussing now, say phi m greater than phi s condition, what you can find in the book, but I am not really confident to tell you about that phi s is not a constant, so I am not recommending. But whenever you read book, different book has a different approach, so don't be confused on it. This is the one condition people are actually written on the book, and that is called the phi m by phi s. So you can understand, this is my phi m, this is my phi m, this is my whole phi m, okay, and this is my phi, so this is my phi s. As per the book, this is my phi s, right? So you can see that phi s here, phi m greater than phi s, and that's why people are writing. Now, what I'm doing, what people are doing, so okay, another thing is that whatever I'm discussing, it is ideal semiconductor, ideal metal semiconductor junction, which is called the Schottky model. Okay, so a metal semiconductor junction diode. So, and these all are actually what I'm discussing about Schottky model. Great scientist, I think. Or ideal, or whatever. So this is my Schottky model, whatever I'm discussing. Now, what I'm trying to tell you, that when you have defined your parameters, fantastic. Now, what you have to do, you have to just join metal semiconductor junction. Join means it's totally different, because it's not that you have a metal and you have a semiconductor, you just touch each other, doesn't mean it's a Schottky junction, right? So this joining process, whatever, it has a particular rules and regulation, right? It's like you have a semiconductor, then you have to like metallize, you have to deposit metal, and then you have to anneal, and during the anneal process something will happen, and then you will form a particular nice metal semiconductor junction, which you will read from the micro nano fabrication technology. But it has a particular rules and regulation. But what I am trying to tell you, that now you have a metal, you have a semiconductor, now you form a junction. When you form a junction, what will happen? Look at that. So now look at this part very carefully, because this is the things that it is just similar to your PN junction diode. What will happen? The moment you join these things, the moment you form a junction out of this, so your electron, because electron, this Fermi level is in higher energy state, you see, then your Fermi level of your metal, or whatever you can think, your EC is higher from that. Anyhow, so your Fermi level is higher position than the Fermi level of your metal. So now look at that. Why it is so important? Why I am telling about this part? So look at this thing. Just conceptually, you have a higher Fermi level. What is the significance of Fermi level? Bottom of Fermi level, all energy states are filled. Bottom of all energy states, bottom of energy, all energy states, whatever, filled. Okay, so now this means like you have a higher energy state. This EF is actually kind of a higher energy state. It will try to fill up this energy of your metal, whatever. Okay. So what will happen, since this EF is higher energy state than the EF of metal, electron will jump from or will come from here to here. Okay, so if electron comes from this side to this side, so what will happen finally? So can you please tell me what will happen formally, whether electron will bend up, the band junction, band diagram will bend up or down, like how it looks. Conduction band will bend up or down. Can you please tell me?
Sir, up.
Yeah. Very good. So let's draw it. And let me draw in this manner. No, I need space. I need space. Okay, so this is my EF. Okay. And suppose this is my junction. Okay. This is my junction. What I have seen you that you have told some that it went up. Okay. Okay, so just for continuity. So let's draw phi m. Because phi m, anywhere phi m is constant. Okay. Similarly, chi is the electron affinity, that is also constant. Now you see your conduction band has moved down. So what will happen? Your chi also like anything else I have missed? No. Now let us draw. So now what it means? Now you have this band diagram. When you have a proper metal semiconductor junction, which I am saying ideal junction, which I am saying it's a Schottky junction, which I am saying no, it's an ideal junction. Okay, let's see whether it's a rectifying or ohmic contact. Let's see. So what you have to do, you have to identify two parameters over there. Look at that. Suppose if you have an electron out of, you have an electron out of here, so it means so if electron wants to go from metal to semiconductor side, if electron if electrons wants to go from metal to semiconductor side, it needs to cross this amount of energy. Okay? So that's what if an electron wants to cross the junction, means if some electrons are there in metal side and it wants to go to the semiconductor side, okay, it has to cross this height, which is called a phi bn. So let me draw, because I am just very important parameter. So it is kind of barrier height from metal to semiconductor. So let me write somewhere. It is here. I am writing 5Bn barrier height from metal to semiconductor. Okay, so this similarly, if you look at this part, that other part, like if some electrons are over here, okay, and if they want to go from semiconductor to metal side, they have to cross this amount of barrier, right? So which I am calling it VBI. No, sorry, because I have to draw in energy scale. QVBI, built-in potential. So now here is what I have done. I have just see that ultimately my electron either from metal to semiconductor side or semiconductor to metal side. Correct. In this case, the connection is actually disrupted, disconnected. So may I know how far you have followed me?
Sir, till QVBI.
Okay, so okay, I have not lost 2 minutes. So thing is that, so you have considered two carriers. So definitely one carrier is there in the metal side. So if these carriers try to go from metal to semiconductor side, it has to cross the 5Bn. Similarly, some carriers are there in the electron side, and if they want to go from, some carriers are there in semiconductor side, and if they want to go from semiconductor to metal side, they have to cross this VBI, which is nothing but built-in potential. So this term, I think you are really familiar with PN junction diode. Built. Okay. From semiconductor to metal, right? So these are the conditions. Okay. Now here, now what is the value of 5A? I mean, like if somebody asks you, okay, how do you conclude? So let us write, okay, 5N. So 5N means high end okay. So you see that from this whole thing is 5N. So from here to here, you see that from here to here, if you see that part from here to here 5N, and this from here to here, it is actually chi. You see, because the top of the EC, so 5Bn, 5M minus chi is actually 5Bn. What's about QVBI? IBN minus EC minus EF, right? So this is my QVBI. Okay. So any question out of this is very simple, I know. Any question up to this level?
No, sir.
Okay. Now what? So this whatever we have done, this is in equilibrium condition. What if you apply some voltage, and what would be this condition and how it varies actually? So now let me draw. So voltage condition. So if you see that's under voltage. What is that? So suppose you have this part. No, I have to be very careful now because I have to draw a lot of things here. Okay. Look at this. This is the structure. If you see that book, paper, so they are representing in this manner, right? They are not drawing everything full. But actually they are drawing the whole thing. So now they are not drawing that vacuum level and everything they are drawing. Now what I am trying to tell you, now suppose okay, so here actually no, I have to write something else which is critical. Let me write. Case 1. Equilibrium. So let me draw the equilibrium condition which we have just now discussed and try to find out few parameters. Okay. So what I'm trying to tell you, like, just remember your period, like our last semester discussion, and thing is that we also discussed, like, if you have a PN junction diode or any type of materials, how to calculate the carriers. You know, when you have a density of states, you have a Fermi level. When you multiply, you will get a carriers, right? So let us draw the carriers in the semiconductor sides. So it would be like that. So if you just remember or if you just recall, this would be carriers. Now these carriers, you can see it is flowing from metal to semiconductor side, right? Because as per our convention, you please remember that we have a metal on this side. We have a metal on this side, semiconductor side, right? And so we have a carriers on metal. Okay. Now I have to draw the carriers in the semiconductor. What I'm trying to tell in this curve, like, you have a metal to semiconductor, correct? And what is the current? So suppose if you want to get a current, what is the current across G equilibrium is actually, you can write J semiconductor to metal. So let me write, okay, semiconductor to metal minus metal to semiconductor, correct? Net current, see, remember, just think about our last semester discussion. You have a piece of semiconductor, okay, and you have a lot of carriers. Suppose the semiconductor is doped by 10 to the 15 per centimeter cube. Plenty of carriers are there. And when you probe a multimeter, you are not getting any current. Does it mean that the electrons are not moving? No. It means the electrons are moving simultaneously, but it has a some cross mover. Like electrons are moving, it is also balanced by something. You have a PN junction diode. Just simply you take a PN junction diode. When you just try to see what is the amount of current is flowing between P type to N type or N type to P type, without giving any voltage, you see it's almost zero. Why it is zero? It doesn't mean that it is always zero. No, because if you take a PN junction diode, the N-type semiconductor you have a plenty of carriers are there. They are actually moving. So it doesn't mean the current is zero. Net current is zero. Absolute value of currents are not zero. Absolute value of current is not zero. Net value of current is zero. And that is what I'm trying to tell you, that you have a metal to semiconductor and some currents are flowing this direction. No, definitely. But from semiconductor to metal, so equal amount of current is flowing the other side, and that is why you are getting, so metal to semiconductor some current and semiconductor to metal the same amount of current, and you are getting actually kind of balancing each other, and that is why you are getting the semiconductor to metal minus metal to semiconductor is zero. Individual value is not at all zero. We have calculated. If you remember, we have calculated this value. Individual value we have calculated, right? Just remember your last semester discussion, right? Individual value of drift current is never be zero. It is like a few milliampere, 78, 92, like a milliampere. Ampere, not milli, even ampere. Individual value never be zero. Net value is zero. So here also, but when you probe it, a metal semiconductor diode or Schottky diode or PN junction diode, without giving any voltage, you are getting a zero current. Okay. So because of what? Because whatever current is, whatever electrons are flowing metal to semiconductor, same amount of electron is flowing from semiconductor to metal, and they are balancing each other. And that is
Sir,
so
which one is diffusion? Which one is drift?
here nobody, nothing would be drift and diffusion because it's a metal semiconductor. So let me discuss this part. Why? Look at the things about, you have a metal side, you have some carriers. Okay, let's go to the other side. You have a semiconductor and it is an N-type semiconductor. Just remember, you have an N-type semiconductor. When you suppose by any chance, this semiconductor side, okay, from semiconductor side, some current is going to metal side. What will happen? This semiconductor side, some electron is there, which is nothing but majority carrier. Because I have taken N-type semiconductor. Electrons are majority carrier. Now it is actually experiencing the environment of majority carrier. The moment it cross the junction of semiconductor, it reaches metal. Now, when it reaches metal, it is also experiencing same environment. Like when electrons in the metal is kind of majority carriers. Look at that behavior in a PN junction diode. I'm just giving an example. Like, so PN junction diode, you see, you have a P. Okay. When this electron, some electron, why it is actually diffusion? Just think about when some electron cross this junction. When this, so N-type semiconductor, you have a electron over there. N-type semiconductor, you have an electron over there. Okay. Now electron is actually majority carriers. The moment it cross this junction over here, now the electron is p-type semiconductor. Immediately electron realize it is no more majority carrier. It becomes a minority carrier. Whenever it becomes, you have applied some voltage, no, somehow you have applied. So it is happening, what I'm telling you, it is happening maybe forward bias voltage. So when electron actually comes from N-type semiconductor, So electron come from the n-type semiconductor, which is nothing but a majority carrier. The moment it reaches to p-type semiconductor, it immediately realizes it is no more majority carrier. It becomes minority carrier. So what he has to follow? So the moment it becomes the minority carrier, it has to follow the diffusion rules. So whatever current you are getting PN junction diode, it is because of diffusion. Right? It is because of diffusion current. Why diffusion current? Because the moment electron comes over here, if you can remember our graph, our drawing, you see here electron diffuse out. Okay. So why it is diffusing out? Because the moment electron comes from n-type to p-type, it realizes it becomes a minority carrier. So there is no other way. It has to diffuse out. Right? So that is why diffusion, and whatever current is getting, we are getting, it is a diffusion current. Just think about. Now look. So now look here. Here you have a p-side diode, and you have a n-type semiconductor. You have a metal. So initially there may be some density gradient. And because of that, electron will come from high energy state to low energy state. So here and it try to balance each other such a way at equilibrium state so that the net current is zero. Now that is the equilibrium condition. No? That's what we are always following. Hello, class next. Class next. Okay. Now, so once you establish the equilibrium stage, now even after that, which I am going to show you, when you apply more electric suppose you have applied some electric voltage over there, electron will flow each other, maybe, but it never became a minority carrier. So because it always become a majority carrier, because electrons in semiconductor site, electrons in n-type semiconductor site is majority carrier. When it transferred to metal side, that is also, it experiences the same environment, right? So it means, so the electron behavior would be the same in n-type semiconductor, electron behavior same in the metal side, right? And that is, and it is nothing but majority carriers, and majority carriers are having higher speed. That is one of the reason people are telling that Schottky junction is having higher speed. Why? Because it never realized, it never become a minority carrier. The moment you have a minority carrier, you are limited by the speed, because minority carrier diffusion is actually low speed phenomena, which is happening in PN junction diode. But here majority carrier device, for majority carrier device, it is a high speed phenomena. The moment you apply some voltage, your electron or holes will move very fast. There won't be any diffusion, there won't be any time lagging. So if you see that which part is drift and which part is diffusion, in Schottky junction diode, there is a no called the diffusion component in the current. Just you follow it, you will see. The moment I apply some voltage. Now case 2, I'm just applying some voltage. Okay, so apply some voltage over here. What voltage? So, okay, another thing is that what is the electric field, plus minus? Okay, so what is the built-in potential polarity? So can you please tell me the built-in potential polarity? So this is my plus side this is my minus side, correct? Because electron has flown from semiconductor side to metal side. So you have an electric field in this matter. Now, if you want to, so this is actually EVBI, right? Now, if you want to make this junction forward bias, you have to apply counter electric field, which is actually this one, right? So V applied or V forward bias, whatever, right? So if you want to apply the forward bias, what would be the your so plus minus. So what will happen if we apply some voltage? So voltage across this junction. So first thing, here few things that you please remember, because that often we have a problem. Just remember your graduation level. Just remember your graduation level practical experience, practical class. How you are giving the forward voltage? Just can you remember? You can give a forward voltage in the following manner. That's what you are doing. You are actually connecting one terminal, which is ground terminal, to any of this probe, any of this part, and other terminal, it may be positive or it may be negative to the other side. What I'm trying to tell you, if it is a two probe measurement, okay, two terminal measurement, you are not really giving negative or positive. You are actually doing everything with respect to ground potential. Now the question is, what is the difference that if we do this experiment with the ground potential or minus plus minus? There is no absolutely, though there is no difference, because absolute value of potential doesn't have any meaning in the semiconductor industry. The meaning is the relative potential. You have a positive terminal, you have a negative terminal. What is the relative potential I'm giving? For an example, like if you giving 0 to 10 volt, it means same thing for me. So if you apply minus 5, sorry, plus 5, okay, plus to minus, so it's like that. So if you are giving 0 to 10 volt, it is having same meaning if you have a plus 5 or minus 5. Okay, so relative potential means plus 5 minus 5. So it is a 10 volt, right? Or same thing I can write, you can give 8 volt or 2 volt. So what I'm trying to tell you, the relative potential matters over here. So that is why though you are telling that when you are giving forward bias, it means like negative terminal to your negative terminal to your negative counterpart, negative terminal to n-type semiconductor, positive terminal to p-type semiconductor. So it is not really true. Actually, you are giving a relative potential. So what you are doing, negative terminal to n and other side 0, something, or you are doing other way. If you want to make it forward bias, what you are doing, 0 to negative potential, 0 to negative terminal, and positive to your p-type semiconductor. That's what you are doing. So what I'm trying to tell you, that relative potential matters over there, not an absolute value. Okay. So here actually, let us, to understand this phenomenon nicely, let us see that I am applying 0 to 10 voltage. So this side is actually I am giving 0 volt, and this is actually minus 10 volt. Okay. And then what will happen? It becomes what is called forward bias. Now, if you apply forward bias over here, So what is the consequence that it will happen? Look at that. When we had a discussion always, so you will see that we are always doing all the plot of our band gap in band diagram in this zone. So it is a zero potential and this is my energy. If you remember our discussion last semester, so everything it is like our this part, right? So now if you are giving minus 10 volt, that is in voltage, what is there in the energy scale? Energy scale is actually energy is equal to minus QV, correct? So in the energy scale, what you are getting? You are getting minus 10 volt QV. So it is actually 10 electron volt, right? That's what you are getting. So that means positive, but you are drawing everything here. That is a convention. You are drawing everything here. So that means positive. You are actually positive 10 volt. That means you are going move towards the zero side because this is my zero reference. This is my zero reference, right? So that means energy scale. The moment you apply minus voltage, it goes up, right? So this portion has to go up, right? So let us draw the modified band diagram under forward bias. Okay. Now you draw the energy. So earlier when it was in equilibrium stage, you remember these things are balancing each other. Okay. Now, the moment you apply voltage, maybe your balancing is happening over here. Okay. And so J2, forget about the direction of current. So normally what happens, the electron flow and the current direction is opposite to each other. Let's forget this convention, okay? Because we are actually going in details of physical phenomena, physical importance or physical whatever. This is semiconductor to metal, okay? So definitely whatever is there down this line, is actually cancelling each other, definitely. But you are getting current only because of this. Because that is the, so this is actually J semiconductor to metal minus, okay, J semiconductor to metal minus J metal to semiconductor. Right? So you are getting current because of this. Okay. What would be the amount of current will be doing, but this is what happening when you apply some voltage. Now this way analysis you have not done for PN junction diode. Your homework will be doing the following, which I am telling you. Same way, what I have drawn over here, the metal semiconductor, they are balancing each other. When you have same way, you have to do on PN junction diode. I hope it will clear a lot of confusion, because this is a different type of analysis that we are doing first time, but this is the best way to understand the Schottky junction diode. Okay, but definitely why we have not followed PN junction diode, because if we try to follow these things in PN junction diode, it looks very complicated, very complicated. It's not so easy, because there is another term called the magnetic areas also coming, which I want. So that is why we have not follow this method in the PN junction diode. But it doesn't mean we cannot do. Once we know the process, then we can do. So that's what I'm asking you to do now. Okay. But it is easy to do it metal semiconductor junction diode because it is only one type of carriers, that is time handling. Okay. Now, this is what happening. Look at that. In this case, whatever you are applying, metal semiconductor or semiconductor metal, whatever you are doing, okay, your metal semiconductor level or this level won't change much. You are not changing the metal side EC or this value. What I'm trying to say in this process, this process, the EF side for metal or metal side, this EF side of metal or whatever, sorry, EC side, we are not changing. Because whatever change is happening in the semiconductor side, nothing is happening to the metal side. Why it's not? Why we are not changing metal? Look at the metal is having plenty of carriers, plenty of electrons. Okay, if you apply little bit of voltage, definitely you are not going to apply 10 volt. No, for Schottky junction diode, what is your threshold voltage? 0.7, 0.8, hardly 1. So you'll get a nice current up to 2, 3, 4, 5 volt. Maximum you can go 5, 6, 7 volts. Okay. Not anyhow. So whenever apply you some voltage across your metal side, okay, since the current electron density across the metals are really high, right? So to get, so this can easily be adjusted. Means like if you give little bit, so since it is having lot of carriers across the metal side, okay, so your EF position won't change too much, because what will happen? EF position change means something else. Like no, you are you are getting lot of carriers from semiconductor side. I do understand. There is absolutely no problem. But it is like adding some cup of tub of like cup of the bucket, or like adding what to say, like you have 1,000 number of atoms or 1,000 number of electrons. You are adding 2 more number of electrons in these buckets. So it doesn't change anything. Metals is already have plenty of electrons. Moreover, if you add some number of electrons from semiconductor side, doesn't mean that you are changing the EF level. EF level won't change because it's already having some lot of carriers. So it is like a bucket of water into the ocean. Does it mean the ocean level will change? Ocean level or sea level will change? Won't change, right? Because metal is already having lot of carriers. Over that, if you are adding some carriers which are coming from semiconductor side, due to the applied voltage, it doesn't change the metal level Fermi level, metal side Fermi level. Okay. So already, so that is why it is kind of fixed. So that is, and now here there are few things that people are saying. So let us try to plot that. So you are going to get a current. Okay, just 1 minute. Huh? Yes, ma'am. Hello. Binde, ma'am. So what we have to do? So let us see J net current. Hello, madam. Yeah, so I'm taking class. I'm sending my students. They will come with this poster. Okay, I'm sending, ma'am. I'm sending within 10-20 minutes. Okay. Me and what? Whom? No. My thing is totally different. My thing is gas sensor for human space program. Maybe Sudarshan ka thing is Priyadarshan sir. But my thing is totally different. It's yeah. Okay, ma'am. I'm just okay, ma'am. I'm asking to see you. Anjit is there? Okay. Yeah, Nisha, Anjita is there? Yes, please give it. Anjita, you and Sonali has to take the poster and all our gas sensor. Now report to Vinda ma'am now itself. Director wants to see. Okay. And you also get your details like when you want to be there in the chairman meeting and what is the process. Okay. After the class, I'll come there and I'll have a discussion with Vinda. Okay. But now immediately you have to move there. Okay, fine. Because I want to finish it before register come. Okay, fine. Go ahead. Call Shonali also. Both have to go. Today's our chairman visit is there, so we're a little bit busy. Anyway, so what is the total current? So net current, if you see J, okay, semiconductor to metal. I'm just forget about sign and everything. We'll discuss about this thing later on. Just suppose this is the things that we are going to discuss. Now, what books are telling you? Books are telling you this metal to semiconductor current. Okay, so just it is a chicken egg problem. So let me go back. This metal to semiconductor currents. Let's go back to the equilibrium stage. Let's go back to the equilibrium stage, and here this metal to semiconductor current. Okay, let's represent it J0. At equilibrium stage, metal to semiconductor current, let's represent it as a J0. Okay, and now you define that J0 in such a manner like why J0? Okay, fine. Why that will clear immediately because I have represented J0 and I am telling it J0 is the current from metal to semiconductor, number one. Number two, J0 is the current from metal to semiconductor whenever there is no applied voltage. So what I'm telling, J0 is the current from metal to semiconductor. J0 is the current when there is no current, and J0 is the current when there is no applied voltage. Okay. J0 is the current when there is no shift of Fermi level. So this is called J0. So again, I'm just refreshing it. J0 is the current from metal to semiconductor equilibrium. That's what I am writing J0 equilibrium. Just think about, huh? And no shift of Fermi level. You can say it is quite trivial, no? Since it is equilibrium, so there is no shift of Fermi level. I do understand, but look at these things. When you apply some voltage over here, the metal semiconductor current is also not changed, right? Because there is no shift of your Fermi level. Again, I am telling, when you apply forward bias voltage, there is no change of Fermi level across your metal site. So that means this metal semiconductor current, metal to semiconductor current, is the same current. The metal semiconductor current is the same current what we have considered across the equilibrium condition, and we can represent it as a J0. Okay. So that is why let us represent J net semiconductor to metal minus J0. Right? Now look at that. J0 has another name. Reverse saturation current also. Why? And that I am going to discuss. One thing is clear, the J0 is the same. J0 is nothing but a current from metal semiconductor side, number one. Number two, it is always fixed. Whether it is in equilibrium or it is in forward bias, or I am going to show you reverse bias, that is always fixed. So J0 is the equilibrium current. First, second thing, it means J0 doesn't change with applied voltage. So that means when you keep some voltage, J0 value doesn't change. Okay, so let us let's try to see what is happening. Let's try to see what is happening when you keep a forward bias voltage. So I'm not forward bias voltage means convince yourself complicated. So I have to draw it very carefully. I have to draw her. This is your reverse saturation current. Now let us grow. This is the current is flowing and that is J0. That you understand. But this side there is no current is flowing because this semiconductor side, it is so deep. It is so deep. So there is no contribution because if you want to flow a current, the electron has to jump the barrier height. But it is in so deep, so there is no current component, correct? So that means, can you remember your PN junction diode or Schottky diode consideration? You are always saying that if you apply some reverse bias condition, deep reverse bias condition, only reverse saturation current exists. Can you just remember? And that value is equal to minus J0 or something. That you remember, no? Just remember this value. But that physically it is coming from here because semiconductor to metal side, there is no contribution. Only J0 has a contribution. And that is why it is called reverse saturation current. This J0 is called reverse saturation current because if it is a deep reverse bias, you have only one current component and that is actually J0. And J0 value is always constant. So it is kind of saturated value. Correct? So that is why it is called reverse saturation current. Okay. So that means in this condition, if you try to draw or try to write the condition as like J net, J semiconductor to metal minus J metal to semiconductor. Semiconductor metal for reverse bias. Metal to semiconductor J0. Okay, so this is actually quality understanding, but at a physically you have to be very sound on it. The sound part is that if you have a 5N, the 5N value is not changing. 5N value, because look at this here very carefully. Here, this value, this is nothing 5N. This 5N value is independent of voltage. And that is why reverse saturation current doesn't depend on voltage. Because reverse saturation current, which is called J0, it depends on 5N. And 5N doesn't change. So you'll get always a constant value J0. Correct. There are, and now what is the actual expression of J0 quantity? Because that's what physically you understand. Now we have to find out J0 expression and everything, which I'll take care next tomorrow. Okay. But till now, you please, because I have to discuss something more like ohmic and Schottky, ohmic and rectifying diodes, which I have not come yet, which I'll be discussing tomorrow, and then I'll discuss with the complete formula of IV characteristics. Okay, that expression I have to try. So up to today, it's a kind of physical thing that we have understood. Tomorrow onwards, we have to go for the detailed derivation. Okay, based on that for the IV characteristics. Okay, so now I'm stopping over here, and please let me know what if you have any doubt. Please.
Sir,
Yes.
sir, it will be very helpful if you share your records, video records, for revision also, because sometimes we get disconnected and we lose the portion that you are
I
teaching.
think you all are here. No, I have described, but I have also come back. Okay, I'll share, but I'll definitely share. Not today. What I want you to, whatever I had a discussion, you just go back and read book. What I feel last semester experience that you are hardly reading book, which is not good. There is no parallel route. There is absolutely no parallel route. So please read book, and then, because whatever I told, it is there in Streetman Banerjee. Now whatever I discuss, you just do it. And I'll send these things after a couple of days, after 2-3 days, all the video lectures, but not now. You need to have some practice to read book. Okay, fine.
Okay, sir.
I'm just urge you, please go back and read book. There is no parallel route. There is no alternative. Reading book. Please go back and read book. Okay. Definitely the way I have discussed, it's nowhere in the book except one book, that is Anderson book, because I am discussing Anderson formula. And that is, unfortunately, this book cost around 10 to 20,000, and I have a one copy and which I have lost. I don't know where I have kept, but anyhow, fine. Discussion is fine. But what I told that you can find out Streetman Banerjee or SMZ. Just go back and check whether it's matching that discussion or not. But forget about video lecture. That definitely I'm going to share you. But at least you please go and check books. At least see how your book looks like.
Yes, sir. Sure, sir.
Yeah. I'll definitely next week. Today I just did something called the arranging of video lectures, but definitely I'll do. Okay, fine.